have midterms? Is it next week or is it the week after that?
It's not next week. I don't know for sure it's week after. Let me look.
Wait, are there 12 weeks or 16 weeks? I think I'm wrong. Oh, there's 4 months, not 3 months. Okay.
Yeah, that's the case.
So midterms are the week of October 9th. Week of October 5th through the 9th.
Are you going on the 9th?
The 10th open the day of deer season.
Wow.
Every Thursday, I've been like doing all much homework as I can, so I've been going archery hunting on the weekends.
I'm going to close the door so we don't hear everybody walking by. Okay, let's do attendance real quick. Okay. Kingston?
Here.
Awesome. Trevor?
Here.
Awesome. Parker? Here. Chase? No Chase? Okay. Karina?
Here.
Great. Darren here. Brooks here. Zachary. Pine here. You online? Nope. Porter?
Here.
Great. Susan's here. And Michael's here. Okay. Today, we're going to talk about boiling water reactors. Okay. Lecture. Okay. Boiling water reactors. There are 32 in the US. You guys remember, is this more or less than pressurized water reactors? Less, a lot less. Pressurized water reactors are by far the standard in the US. Hello. Just like pressurized water reactors, we typically use the same fuel, cylindrical UO2 pellets. That is the standard in light water reactors, which boiling water reactors and pressurized water reactors are both types of light water reactors, because light water is what we use for our moderator and our coolant. This would be compared to a heavy water reactor, which is what they use in Canada, and they don't enrich their fuel. They essentially enrich their water and put more hydrogen in it. And so they use slightly different fuel, or a liquid metal reactor, which would use lead or sodium as a coolant. Bundles are about 12 feet tall, and that can be arranged in groupings of 6 by 6, 10 by 10, or 11 by 11. So the fuel bundles are smaller than the arrays put into a pressurized water reactor. They contain 370 to 800 assemblies. There's a huge variation in what you can put into a boiling water reactor. This is because you have to design your physical structure a lot more carefully, because we can't even things out by adding dissolved boric acid, because we're going to boil our water in our core, and if we have boric acid in there, that's going to be left behind as we boil the water, and you're going to get too acidic of a pH in your coolant. You're going to start damaging your structural metals. 4 fuel assemblies and a cruciform control blade in the middle of those 4, right? So it's going to have a cruciform. There's going to be 4 quadrants. Each quadrant is going to have a fuel array assembly. Make a fuel module. There are larger diameter coolant channels in boiling water reactors. This is important because, as you will learn in thermo, when we start having boiling, we're going to produce something called turbulent flow. And so as our steam comes out of its liquid phase and starts to become a gas, you're churning that water. You guys ever watched a rolling boil on a pot on the stove, right? It's bubbly and churny. That's turbulent flow. You need more room for this kind of flow to go between the channels to still effectively create the heat transfer you need, because anytime a large gas bubble is in contact with your fuel cladding, you are not transferring away as much heat, because that heat's transferring into a gas instead of our chilled liquid, right? And so when that water starts bubbling and you have little gas bubbles along your fuel, you can create hot spots. And so to ensure that those aren't along the fuel, and instead that turbulent flow is flowing past and actually increasing our heat transfer, because when you agitate the flow, it transfers heat better, as long as you don't have large gas bubbles against the fuel. And so you just need more room for this process to go through its cooling channels. Okay? Pressure is at 71 bar or about 1,000 psi. Who remembers from Wednesday what pressure the PWR at?
Less than 25?
About twice that. Yeah, about 2,500. So about twice what a boiling water reactor is at. Okay? Coolant comes in at 278 and goes out at 287, because the coolant that gets cycled is not the steam, it's not the liquid that goes through a PWR. You're going to have a small temperature rise, because, again, as you'll learn in thermo, some of this temperature has to go right into creating the phase change instead of just continuing to raise the temperature. The pressure vessel is significantly taller for a boiling water reactor, so that there's sufficient room for as much water as you need and room for the gas at the top to boil. Okay? So here's a picture of that cruciform control assembly. And then here's how it looks when you put it all together with the fuel assemblies and create a module. Okay? So that blade design, they're here at each junction, right, across the whole core, is very unique to a boiling water reactor. And sometimes instead of saying control rods, you will say control blades, especially if you start at a PWR. It's hard to switch over to control rods when you switch to a PWR, because this is such a unique thing at a boiling water reactor.
So the fuel rods, they enter from the top or the bottom?
They're going to come from the bottom, the control blade.
Yeah.
And essentially what they do is they create a sort of push button system that pushes them up, and they'll use water flow or a hydraulic press to push. And so if for any reason you have a power failure or an accident and they stop pushing those, you can get the rods to drop out of the bottom, because they can't come from the top, because that's where our steam is and our steam separator and all that steam process is starting. So they get pushed up into the core from the bottom. And so you have to essentially have an ability to have something drop on that to push them up in order to ensure you get your accident shut down. Does that make sense? It's also unique. Okay. Steam is produced directly inside the reactor pressure vessel, okay? And the entire coolant system at the plant is radioactively contaminated. This is actually a relatively minor concern. Most of the radioactivity that we're getting from our water is when neutrons strike the oxygen in H2O, and they form radioactive nitrogen, nitrogen-16. It only has a half-life of about 7 seconds, and it is the majority of the gamma dose that we get from our coolant water. But essentially, within a couple minutes of stopping the reaction in the nuclear reactor, places where your radioactive steam and water have accumulated will no longer have a dose. It just takes a few minutes for that to decay away once you're no longer producing it. So while it's running, yes, you have that radioactive coolant, you're getting a gamma dose from your nitrogen-16, but as soon as you shut down, when you go to do work during your outage, you pretty much had this decay away. So it's not quite as big a deal as it might otherwise seem. We're gonna take a look at this link here. There's a great little video. Everyone online, can you see that video?
Yes.
Yeah.
Okay. All right, guys, I just realized I didn't share the audio with the folks online. They can't hear it. I'll turn this up a little bit. Sorry, guys, now you can hear it.
The process of creating electricity using nuclear power begins with the splitting of uranium atoms in the reactor. This process, called fission, produces heat. In a boiling water reactor, the water surrounding the nuclear fuel is turned directly into steam in the reactor vessel. The steam is then transferred by pipes to the turbines. The spinning turbines drive the electric generator to produce electricity. After the energy from the steam is used to spin the turbines, it is drawn into a condenser where it is cooled and condensed back into water and pumped back to the reactor to be boiled into steam again.
So, very simply, that is what a PWR does. Okay. One of the things that's kind of interesting is people hear about this contaminated coolant and steam that circulates in the plant at a boiling water reactor, and it tends to be viewed with a lot of concern. However, essentially, we have decades of operating experience that says once we shut down the nuclear reaction that's occurring, we're dealing with about the same amounts of radiation from our steam as you have in a coal-fired plant, because coal ash is actually also radioactive. nobody talks about it, right? So it's roughly about the same amount you're going to have working with coal. So this isn't the huge issue, even though there is some additional expense and concern for the operators of boiling water reactors, especially when it comes to decommissioning. It's not as big an issue as you would initially think. Okay, so here's this diagram. Again, the video did a great job of explaining it. They just didn't mention that this cooling tower is what supplies our cool water to the condenser. So this is still a separate cycle. And so what comes out of the cooling tower is not radioactive. It's still clean water. And then one more, just to kind of give us the layout. Here it is with animation, but I'm not going to stick on that page very long because you guys saw the video, which I think did a great job. Karina, your little green highlight on your box popped up. Were you trying to ask a question?
No.
No? Okay. It's been doing that on all of my classes. I'm not sure why, but okay. So we looked at this video and we saw the for loop PWR, right? So with the PWR, you essentially have your much taller pressure vessel, and at the top of that pressure vessel, above the core, you have your steam separator and dryer. So the thing that was unique about the pressurized water reactor is you had a pressurizer that fed right into it. Here we have this steam separator and dryer. We want to ensure that we have very dry, superheated steam when we take and we put it to our turbine. Because if there's any moisture, we have low quality steam, little water droplets are going to strike our turbine blades and it's going to destroy them. We want pure, dry, all vapor steam. So the first part of that is ensuring that as much of the liquid stays in the core vessel, and we're going to do this separator and dryer process so that we have good quality steam leaving the core and heading down to our turbine process. Yeah.
The steam reheated before it enters.
It is, yes. They're cutting out our reheaters and additional separators and dryers as we go to the turbine. That steam essentially gets treated several times to make sure it truly is dry, superheated steam when we get here to the turbine. And then when we condense, before this water goes back into the core, yeah.
Why is it so important that the steam is like super?
That's the most efficient way to take energy from the water, is to have good quality steam. And also, these nuclear turbines are several $1 million pieces of equipment. And so when you have a bad drying process that destroys your blades, it's not like you can go and pop in blades at your next outage. You're going to need $12 million to make that repair. And utility companies, a lot of them are ultimately for profit, right? Nuclear power plants. And so they don't want to spend unnecessary money replacing that component when we have a very well understood technology that's relatively cheap to do that. And by doing this, we have more efficient energy production anyway. This demineralizer process here after we condense is to ensure that only very clean, correct chemistry water goes back in the reactor, right? This coolant has now circulated through a large number of pipes and gone through several different processes. It could have picked up contaminants. It could have picked up corrosion. Its chemistry could have changed. So before we put it back in the reactor, we're going to ensure that it's the right water that goes back in. Then there's recirc pumps inside, right? Because we're going to have some coolant that stays liquid and continues to get pumped through. Reactors are at a high enough temperature that most commercial power plants can't rely on natural circulation. You have to circulate the coolant. Pressurized water reactor pumps it through that heat exchanger and that's how it recircs, right? Here we have to have our little recirc pumps for that liquid here. And then the control rods, they do come from the bottom. So essentially what happens is the mechanism that holds the drive has a little hydraulic little lift, and that will drop a weight on that to push them up. And so you still use gravity essentially to insert your control rods. They're just not dropping from the top. Does that make sense? Everyone online, you guys following?
Yes.
Yeah.
Okay. Great. So, PWRs have a lot of the same components as a PWR, right? We've got a grid plate, it's just down at the bottom. Control rod drive housing is down at the bottom. We have some spray nozzles for our emergency cooling water spray. We have the same thick pressure vessel, right? We've got a steam outlet nozzle, and then we've got our recirc inlet and outlet nozzles. The core shroud is still this piece that kind of holds everything into the grid plate, right? There's a guide, so your rods come in the shroud and go through the guide, so that they're on a straight path the whole way in between the fuel. So it's a pretty similar arrangement, except that control rods come down here, so we can have our dryer and separator assembly at the top. Okay. So, couple of issues with PWRs. You can still overpressurize, right? Even though the pressure is much, much lower than a pressurized water reactor, we're at 1,000 PSI. That's not atmospheric pressure, right? So we're still dealing with a fair amount of pressure. Specifically, the BWR has to be able to respond to pressure transients because you have a much larger coolant loop and a lot more piping and a lot more pressure changes that can occur because you're not putting a pressurizer on it in the same way. This overpressurization protection is done with a pressure suppression system, which essentially uses safety release valves below the water level, and it just vents overpressure into the water. So as the gas builds up, it just vents that back down into that water, and then you don't have pressure building up inside your vessel. Okay, that water pool that you have looks like a little torus underneath a loop, little ringlet kind of that sits underneath the reactor vessel. I'll show you a picture. And it's called wet well, torus, or most commonly the suppression pool. Okay. There's also an emergency core coolant spray system. Okay. It essentially sprays water from the top of the core right onto the steam separator and dryer. And by having this cool liquid water hit the steam, you are immediately creating a large amount of cooling in your reactor, and essentially going to prevent some of your coolant from boiling away. Okay. If there is a reactor rupture, when we're talking about this pressurization, essentially as soon as you're at the temperatures you are in a reactor without any pressure, all of that coolant is going to immediately flash to steam. You are going to lose all of your coolant instantaneously, right? So the cold water from this torus, even if we have a rupture and we lose it, the emergency core cooling spray is going to condense some of that back to water, and the torus makes sure that some of that pressure remains in the system, okay? So here's what this kind of looks like. We have our reactor pressure vessel, right, that sits on this little structure at ground level. And below grade, there's essentially a little donut that goes around the bottom of the pressure vessel. And this is where our overpressurization can go in, right? So our suppression pool or our wet well. And this part that it connects to is called the dry well. Does that make sense? Okay. I think it's really hard to draw this without it looking kind of, yeah, but that's what it is. Okay. So I'm sorry this text is so small. I'll make sure and say it all to you guys, but I think most of you look at the slides on your laptops and stuff. So main advantages of boiling water reactors. You're dealing with lower pressures, so the construction is easier. You don't need as many specialized high pressure components. The pressure vessel is subject to significantly less irradiation than a PWR because you're not going to as high temperatures, and it doesn't become as brittle with age. So we talked about having to do our core internals change out and change out the pressure vessel. You have to do that a lot less with a boiling water reactor. You're going to operate at a lower fuel temperature, essentially because a large amount of this heat transfer is done by our latent heat of vaporization. You are not going up in temperature as much as you create that steam change because the energy is going into the phase change. So you don't have to create all this sensible heat that you do in a pressurized water reactor. You just get to operate at lower fuel temperatures, which means if you lose coolant and are having an accident and need to keep that temperature low enough to keep the fuel from melting, you're starting at a much lower point to begin with, right? There's fewer components because we don't need a pressurizer or a steam generator. Even though it's pressurized and we do have a little bit of a pressure system, it's much, much smaller, right? It's not nearly as big as the pressurized water reactor. And with fewer systems to operate, you now have an easier plant to operate and qualify on. Okay? You also have a lower probability of a rupture that would lead to a loss of coolant accident. So your likelihood of leaking your reactor coolant out of your reactor is lower because you just have fewer pipes because you don't have to have that intermediate system with the steam generator at all, right? To remove all that piping. You don't need as many large diameter pipes because we're pumping steam now instead of water, and gases will completely fill whatever vessel they're in, right? So we don't have to deal with just as large diameter, which means with less piping and smaller pipes, we don't have to make as many welds. Welds are where we have difficulties at nuclear power plants because you can have corrosion issues and you can have strength issues. They're difficult. So less of them is good. This ECCS system and the presence of a wet well is a very elegant engineering system to provide emergency core cooling. And it's a more robust system than what they have to use for pressurized water reactors. So it's essentially got better safety systems. Not necessarily inherently more safe, but it does have better safety systems. The lower temperature, you can make the argument that there's a little inherent safety in that, but PWR people would probably disagree strongly. Water level in the pressure vessel is the same for both normal and emergency operations, which makes it a little easier and more intuitive to assess your emergency conditions because they're not significantly different. So when you're trained in your normal operation, your normal system status, it's the same when you have an emergency. Whereas a pressurized water reactor, you can lose a lot of that water and still be sufficiently covered. And so now you're dealing with a lower amount of water and you just have different parameters to deal with, okay? You don't use boric acid, so you have less issues with corrosion, even though it's very well understood and monitored in a PWR, that use of boric acid. There's a very famous example that happened while I was an undergraduate. The Davis-Besse nuclear power plant had boric acid leaking out of a fitting around a control rod drive. And as that leaked out and accumulated on top of the pressure vessel head, the water would then evaporate, leaving behind purely boric acid, which is very caustic. And it essentially had corroded so far through the pressure vessel that only a few centimeters of material were left, protecting against a loss of coolant accident, protecting against that pressure vessel actually being open to the atmosphere, right? Which would have been a catastrophic accident. And they happened to find it because after multiple delays of a required inspection, the NRC told them, no more, you have to go do this inspection. And as part of that inspection, they found this huge amount of corrosion. So it was one of the biggest near misses in recent history because they were, if they had delayed it another 3 months like they wanted, they probably would have corroded through their vessel. So removing that does have some advantages, right? Even though it's not a surprise how we handle it in a PWR, and it gives us some really nice advantages, we don't have to deal with any of the disadvantages in a boiling water reactor, okay? Boiling water reactors, because we have our more robust safety system, generally 2 of the 4 redundant components in our safety systems can fail, and we still have an operable safety system. So there's just a lot more failure that can be tolerated and still have our safety systems perform when they're needed. Okay, they're better safety systems. They're made by one major vendor, GE Hitachi. So all of our BWRs are pretty much the same reactor, which means they're extremely predictable. We have very uniform designs. And so if you go work at one boiling water reactor, and then you need to move, you end up at a different boiling water reactor, it's almost exactly the same plant. It's very easy to move between them. It's very uniform. One nice thing about having the control rods at the bottom is that we don't have to take the control rods or drive out of the core when we need to refuel, right? Pressurized water reactor, you open the top of the reactor, you have to pull out the control rod drives and the rods so you can get at the fuel, right? Which creates some unique criticality challenges and safety issues because the control rods being in the core are what prevent us from having a reactor when we don't want a reactor, right? They prevent that critical reaction. Bottom entry, they get to stay in and we can access the fuel from the top. We just move the steam separator out of the way, right? It also allows us to test and do maintenance on the control rod systems a little bit easier because we can have it open and we can still be moving our rods, okay? The hydraulic forces that we use to push the rods up are actually a much greater force than gravity. And so control rods are much less likely to jam partially inserted. This happens with pressurized water reactors. The advanced test reactor, and I know, is a lightly pressurized PWR. It's at a much lower pressure, but it's the same kind of system. And they have problems with their rods sometimes failing to insert all the way or move as well because that gravity free fall has some complications. Not everything falls perfectly straight, right? And so you can get jammed. And even though we have procedures and ways to deal with that, it's just nice to have a system that kind of precludes it from happening as much, right? And then the big reason that boiling water reactors are a good choice for commercial power plants, they are higher efficiency. So when we're building new reactor power plants and someone's already going to spend a tremendous amount of money on building that facility, they're going to get more product for their initial effort with a higher efficiency plant. So a boiling water reactor is the choice there. Okay, but we have some disadvantages too. Because we can't make things a little bit more even with our boric acid solution, the consumption of the nuclear fuel across the core is not quite as even, not quite as predictable. And so the engineers who do the calculations for managing this, creating our outages, creating our refueling schedule, their job is a little harder. And it just makes ensuring that you're getting the most out of your fuel a little more difficult. Because we have two-phase flow, that water and steam mixture, right? More instrumentation is necessary because instruments that work in water and instruments that work in vapor may not work in both environments, right? So we're going to have a few more instruments, and that means you, as operators, have to know when you need to look at which one of these instruments for what piece of information on the system. Okay? The pressure vessel is larger because you have to put the steam separator and dryer in there. So that particular component does have a higher cost. Even though it doesn't have to handle as large a pressure, it's still at a big pressure, right? And now it has to be much bigger than the pressurized water reactor pressure vessel. Again, there's contamination in the coolant all the way to the turbine. So when it's operating, you do have shielding and access control systems that you have to use. Training people to have good ConOps when it comes to access control is really hard, right? You have to be responsible for knowing you can't open that door and go in that area. And if the sign falls off, which happens, like how do you know that that's an area you're not supposed to go, right? So that's kind of a constant issue that you have to maintain and make sure your labeling is correct and put these access control systems into practice, which is done very well, but it's something that you constantly have to make sure is done correctly. BWRs were built first. The majority of our oldest power plants are boiling water reactors. We now have different accident scenarios that we have to analyze and certify that our power plants will survive, right? We have better understanding of what natural disasters actually impact our plant, and things like, Hurricane Katrina. You guys were probably pretty young when Hurricane Katrina hit, but you guys all remember, right? So did you know that there were 3 nuclear generating stations that were knocked offline by the hurricane that within less than a week were able to produce electricity again? They just didn't have a grid to deliver it to. So in contrast to what occurred at Fukushima, right, we had 3 nuclear power plants get knocked offline by the initial loss of power, offsite power, because of the hurricane. And they were ready and able to give power. It was just that pretty much all of Louisiana, southern Texas, and southern Mississippi didn't have a grid to deliver that power to, right? Their infrastructure had been knocked down. The one plant that was a little bit behind had been built at a slightly lower elevation. And so we have a lot more requirements now, as we've learned, that you have to consider longer periods without power, because it's not necessarily that the power plant was damaged, but repairing all that infrastructure, both for Fukushima and Hurricane Katrina, took way longer than everyone had kind of expected would occur, right? There was kind of this idea that when a natural disaster occurs, everyone's going to prioritize immediately returning power to nuclear power plants. Well, actually, the National Guard was busy trying to save people out of the Superdome, right? So they weren't building the grid back up yet. So we just kind of learned some things about how those natural disasters play out. And the original builds are not necessarily able to certify that they're going to survive the same kind of accident scenarios that our new builds are built for. And so we have a gap between our existing older facilities and the new requirements. One of the things that's happening as they relicense plants and do license extensions is they're requiring upgrades so that you meet these requirements. So we're getting there. It's a known issue. We know which plants are the issues, and we're getting to more robust plants. But this is a disadvantage that we have with our current fleet of BWRs right now. Okay. Again, we've talked about this insertion issue. The disadvantage is that you have to have two complete systems here because you don't have the always existing gravity, right? A PWR doesn't have to have another way to insert a rod because gravity always exists. If gravity doesn't exist, we have way bigger problems than our nuclear power plant having an accident, right? But we can't count on gravity. So if our one hydraulic system fails, we have to have a second one. So there's more cost, there's more operational concerns. There's just a bigger requirement here for our bottom loading control rod. Okay. And then of course that two-phase flow, even though there's some real advantages to it, there's just some additional complexity for handling it that exists when you're dealing with a PWR. Any questions? Yeah.
So with like a commercial nuclear power plant that supplies energy to a grid system, like during Hurricane Katrina, do those power plants, once they start back up, do they supply power to themselves as well?
No, they just didn't start back up. They just stayed shut down. If you don't have somewhere for that electricity to go, essentially you're just creating electrons that will accumulate, right? You have to be connected and have that electricity go somewhere. Otherwise, you're going to damage your generator, right? So they just didn't restart until the repairs to the electrical grid had occurred and they had someplace they could put the electricity.
So do they supply power to themselves?
No, so they're actually not allowed to be their own source of power because you're required to have so many backup power systems in order to make sure that you can always pump your coolant in whatever accident, right? So typically nuclear power plants have used on-site diesel generators, and you have to have, so many hundreds of thousands of gallons of diesel fuel in a tank on site, ready to go in the diesel generators that you have to start up and test, every month to make sure that if you lose power, they can turn on automatically and keep your coolant pumping after you shut down for long enough for your residual heat to be dealt with. So ATR just did something recently where they removed their diesel generators, which have a tremendous amount of EPA regulation, right? Diesel generators are not the cleanest technology. So INL went to a battery-backed system, and they have these really fancy battery systems that when all power is lost, they can provide the power, and then they're constantly charging when there is power. So they're a pretty cool system, and they're kind of doing that, to demonstrate the movement to slightly better technology. But like one of the things we do in your third semester is we go tour the on-site diesel program here. You guys can see the kind of diesel generators that are typically used for that. That's still the norm.
I have a question. If BWRs are like really good and they have so many advantages to them, then why don't most power plants use BWRs?
Because of the specific advantages you get with pressurized water reactors, so that ability to go longer between outages because you can use boric acid and you can really carefully control your fuel consumption, That is a huge advantage to commercial power production. And so even though you have some disadvantages, that's a huge advantage in how we operate our fleets. So that one kind of sticks out as a bigger deal than some of the disadvantages you might otherwise see with PWRs. Does that make sense?
Yeah. Mhm.
Okay. So I have just a couple of interesting pieces of current events and information in the industry that I wanted to show you guys. So first of all, this is kind of interesting. Google has announced a green pledge where essentially they're not going to build or put Google locations in areas where the electrical grid is primarily supported by fossil fuels.
Wow.
So by, I don't remember, by 2030, yeah. They're not going to be in any location that doesn't have primarily carbon-free energy sources, which when a company with that much money starts saying they're going to take jobs away from places that use coal and natural gas, then you really have a motivation to get off of coal and natural gas, right? Because now we're talking about big job and money impacts.
So a big problem with like green energy is like being able to store the energy after Elon Musk and Tesla is the world's biggest battery in Australia this year.
Yeah, I'm really interested to see what battery technology does, because right now, wind and solar are, in my opinion, nice ideas, but we don't have the ability to do our base load power generation. And Americans don't moderate consumption. It's just not a cultural value. And so we're not reducing our use of materials, we're not reducing our energy demands, we're continuing to grow that. And so we will always need a significant base load power capability. And right now, the only carbon-free energy that can do that is nuclear, right? So I don't know that Google necessarily means to be pro-nuclear. Sometimes they're not. But what they're saying essentially is that your base load power is going to have to be nuclear or we're not going to build in your state. So I think that's super interesting and has the potential to drive some new construction in states that are not nuclear or have been closing down nuclear power plants, because now they have a real motivation to switch. Yeah.
Do you think that if that doesn't work out, like if the baseload power is mostly green after a little while, because they're not really pro-nuclear or not, they're trying to be green, then they'll kind of redact this statement and kind of go back to where they were?
It's possible. You know, I would certainly hope that what would happen instead is that they would be educated on why nuclear is a green energy and why it's so important as part of our portfolio and strategy. And that as they do the research and are actually trying to make this happen, they get more information, and that would cause them to become very pro-nuclear. But, you know, we've certainly seen that. We've seen that politically several times where different politicians will be pro or anti-nuclear based on one thing happening or not happening, right? So it can go either way. But this is interesting because Illinois just announced that they were shutting down a power plant that had a license extension until 2030. And as a response to that, some unions essentially are working to protect nuclear power plants because there's a tremendous amount of jobs for a lot of unions, electrical, piping, all of these groups work at power plants too, right? So this is a group that has not been as environmentally active traditionally, but they're coming at the pro-nuclear side from a purely jobs perspective. And of course, the green jobs money that Congress is making available in certain things they're pushing. But that was just interesting as a response to a plant shutting down. And then this was kind of great news for people who are up and coming operators. Nuclear power outreach reached 2,657 terawatts in 2019. So that was 10% of the world's total electricity demand was produced by nuclear. And this is the most that it's ever produced in the world. And of course, Asia is going super pro-nuclear, 17% more nuclear generation. China has tripled its nuclear generation in the last few years. So nuclear is growing. It's a growing industry, growing career fields, it's being pushed more and more. So I just thought that was some exciting news to see here. Kind of shows you from 1970 to 2018, just the growth of nuclear generation in different parts of the world.
Kind of off topic, but if we were to start like reprocessing and having like a closed fuel cycle, would we be able to use like our fuel in like storage right now? That's like our spent fuel that we've like taken out of storage and re-put it in?
Yeah.
We would, okay.
Yeah, we would. We'd be able to take out what we're currently calling waste and instead call it feedstock. Yeah. All right, guys, that's all I've got. Have a great weekend.
Thank you.
You're welcome.